Welcome students. We are continuing with the classification of elements and periodicity in properties. So in the previous class we have discussed about the classification of periodic table into S block, P block, D block and F block, and we have studied about the properties of each of the block there. Now moving further here, and let's discuss about the periodicity of the uh, modern periodic table. Okay, so what are the causes of the first thing which we are going to discuss here is the causes of periodicity. Periodicity's causes. Okay, so first let's discuss about what is periodicity. The recurrence of similar properties of elements after certain regular intervals when they are arranged in the order of increasing atomic number is periodicity. Okay, in the modern periodic table it is the periodicity. What is the causes of periodicity? For the properties of element, repetition of the repetition of similar electronic configuration of their atoms in the outermost energy shell after certain regular intervals. It is termed as the periodicity. Okay, here it is the cause of periodicity. Okay, so as we know that in the generally lithium, sodium, potassium. Okay, for this if I am going to see 1s2 2s1 1s2 2s2 2p6 3s1 1s2 2s2 2p6 3s2 3p6 4s1. Okay, so here we will see that the repetition of same kind of nature is being seen out here in this type of element. So this thing shows the periodicity here. Okay, now we are going to study about the trends in the physical properties of the elements in the periodic table. Okay, trends in the physical properties of the elements in the periodic table. So first we are going to see the atomic radius as the physical property. Okay, we are going to compare the atomic radius as the physical property for the different elements in the periodic table, and what is the trend which has been followed out there. Okay, so what is the atomic radius? The distance of the center of nucleus from the outermost shell of electron is called atomic radius. Okay, it has been termed as the atomic radius. Generally, the size of an atom is approximately 1.2 Armstrong. That is 1 Armstrong means 10 to the power minus 10 meters. Okay, so 1.2 Armstrong, that can be written as 1.2 into 10 to the power minus 10 meters. Okay, according to the probability picture of electrons, an atom does not have well-defined boundary. Okay, if I am going to see according to the electrons, then an atom does not have any well-defined boundary. The probability of finding the electron is never zero, even at large distances from the nucleus. It is not possible to isolate an atom and measure its radius. So the probability distribution of atom is also affected by the presence of their atoms in their neighborhood. Okay, what does this means? That it is not easy to measure the atomic radius of a single atom by isolating it with other atoms. Okay, so the probability has been taken out for their atomic radius by seeing out the neighbor atoms, okay, which is present around there. Size of atom also changes from one bonded state to another bonded state. We will see that the size of the atom changes there when it is formed. It is forming one bond state with another bond state, and this is known as effective size. That particular size of that atom is known as effective size. Now let's discuss about the atomic radius of hydrogen atom. Okay, so hydrogen atom is always formed in the form, in the dihydrogen form. Okay, so in the dihydrogen form, what will happen here? We will see that two hydrogen atoms are intersected with each other, and here the radius of the half of the distance between, okay, half of the distance between two centers of the hydrogen atoms will be termed as what? It will be termed as the atomic radius here. Okay, atomic radius. So here the atomic radius will be 37 picometer for hydrogen. For H2 it will be 37 picometer. Okay, the distance between the center of nucleus of the atom and the mean position of the shared pair of electrons between the bonded atoms, it is the atomic radius or the covalent radius. Is it the covalent radius? Okay, so the definition for covalent radius is better, the distance between the distance between the center of nucleus, the center of nucleus of the atom and the mean position and the mean position of shared pair of electrons, of the shared pair of electrons between the bonded atoms, between the bonded atoms is called the covalent radius. Okay, it is termed as the covalent radius. Next is the metallic radius. Okay, next is the metallic radius. The definition for metallic radius is one half of the one half of the internuclear distance, one half of the internuclear distance between the two neighboring atoms, between the two neighboring atoms of a metal in a metallic lattice, in a metallic lattice is called the metallic radius. Okay, this is termed as the metallic radius. For example, the distance between two adjacent copper atoms in a metallic copper is, okay, for copper this distance is between two different atoms of metal, between two different atoms of copper in a metallic lattice is 256 pm. Okay, picometer, 256 picometer. Okay, so here the radius will become 256 divided by 2, that is 128 picometer. This will be the metallic radius for copper. Okay, so what will be the variation in the periodic table for the atomic radii? Okay, what will be the variation of the periodic table in the variation in periodic table for atomic radii? Atomic radii. First, variation in a period. Okay, first in period, which kind of variation will be seen out there? So there we will observe that the atomic radii decreases with the increase in atomic number. Okay, in the period we will see that the atomic radius will decrease. Atomic radii decreases with increase in atomic number. With increase in atomic number along a period. Along a period. Okay, it means that if you are moving left to right in a period, in a periodic table, then the atomic size will be decreasing. Okay, atomic size will be decreasing. It means that for lithium, it will be having more size as comparison to that of the fluorine, because they both are present in same period, and lithium is present to the left hand side of the periodic table, while the fluorine is present at the extreme right hand side of the periodic table. So hence, the size of the lithium will be larger than that of the fluorine here. Okay, next the next let's discuss about the van der Waals radius. Van der Waals radius. One half of the internuclear, one half of the internuclear distance between internuclear distance between the nuclei the nuclei of two adjacent atoms of substance belonging belonging to two neighboring two neighboring molecules in a solid state, okay, is called van der Waals radius. This particular thing is called van der Waals radius. Okay, so how to geometrically explain this thing? Okay, so geometrically we can explain this thing by the funda that, okay, two atoms I am taking, which are doing the structure like this. Okay, and two more atoms are there. So here we will see the distance. Okay, so the total distance between this particular two van der Waals, this is for chlorine. Okay, one Cl2 and this is two second Cl. So the different distance between the two different molecules, okay, two different dichlorides, here it is 360 pm, 360 pm, and here the half will be 180 pm, which is the van der Waals radius. Okay, this is the van der Waals radius. This is the van der Waals radius. Now next, it may be noted that the inert gases such as argon, okay, or the helium, okay, they do not form any chemical compound, and therefore their atomic radius is usually expressed as the van der Waals radius only. Okay, their atomic radius is termed as the van der Waal radius only, and they are also termed as inert gas radii. Okay, they are also termed as inert gas radii. Next is the variation in group, the atomic radii of. Okay, now let's talk about the variation of atomic radii in group. Variation in group of our atomic radii. So on moving down in the group, on moving down in group, the shells in atom increases. The shells in atom increases, and hence the atomic radii increases, and hence the atomic radii also increases. Okay, due to the increase in the number of the shell, there we will see that the atomic radii is also increasing out down in the group. Next, we are going to talk about the ionic radii. Ionic radius. Okay, ionic radius. What is ionic radius? So the effective effective distance from the center from the center effective distance from the center of the nucleus of an ion up to which it has an influence in the ionic bond in the ionic bond is called the ionic radius. Okay, it is particularly termed as the ionic radius. Okay, so here we can represent ionic radius such as if two atoms are ionically compounded like this. Okay, if two elements are ionically compounded like this, then here the half of the distance between this O and O dash will be termed as the ionic radius. Okay, it will be termed as the ionic radius. So we will see that the radius of positive ions is always smaller than that of the parent atom because they have loosed out the electrons there, and the radius of the negative ions will be larger than that of the parent atom because they have accepted the electrons there. Okay, so what is the trend here for the what is the trend here for that of the atoms in the the radius, ionic radius for the elements in the periodic table? So on moving in the period, on moving from left to right in the period, we will see that the ionic radius, okay, the ionic radius is decreasing out there. Okay, in period, in period on moving from left to right, the atomic size decreases, the ionic radius decreases, for the corresponding elements there. Okay, as we are moving from left to right. Similarly, on moving down in group, we will see that the ionic radius is increasing. The ionic radius has been increasing out there. Okay, so these are the different trends for the atomic radius, ionic radius for an element in the periodic table. Next particular property, physical property, which we are going to discuss here is the ionization enthalpy. Ionization enthalpy. So first let's discuss about what is ionization enthalpy. So energy required, the energy required to remove an electron to remove an electron from isolated gaseous atom in its ground state, in its ground state is called ionization enthalpy or ionization heat. Okay, ionization enthalpy or ionization heat. Okay, so ionization enthalpies can be more than one for a particular atom. Okay, it depends on the oxidation state of that particular atom. If only one electron can be removed out, then that particular ionization enthalpy will be termed as the only ionization enthalpy. But if more than one electrons can be removed out there, then there will be first ionization enthalpy, second ionization enthalpy, third ionization enthalpy. Okay, like this the ionization enthalpies will be present out there. But if we are talking about the first ionization enthalpy, the energy required to remove is very less. Okay, for any atom which is having, let's say, minimum two ionization enthalpies there. Okay, so the first ionization enthalpy will be very less as comparison to the second one. What is the reason behind that? The reason is that after removal of the first electron there, what will happen? The let's say this is an atom. Here two electrons were there in the first shell. So we have removed first electron from here. So after the removal of first electron, what will happen? The nuclear charge of the second electron will be increased out with that of the nucleus there. And due to this reason, what will happen? The second ionization enthalpy, the second ionization energy for the second electron, it will start to increase out there. Okay, it will start to increase here, and hence it will be more difficult to remove that particular second electron there. Okay, it will be more difficult to remove the second electron there. So this is the trend for increasing. When we are increasing the first electron, second electron, third electron, the ionization enthalpy will be increased out there, and hence we will see that there will be problem to remove the electrons after the first one. Okay, then after the second one, more energy will be required to remove the third one, and for the fourth one also this same thing will be seen out. Now, what are the factors which affect the ionization enthalpy? So the first is the size of the atom. The larger the size, the lesser the ionization enthalpy will be there. Okay, factors. If I am going to talk about the factors affecting ionization enthalpy. Okay, factors affecting ionization enthalpy. So the factors which will be affecting ionization enthalpy, the first is size of atom. So the size of atom, the radius of the atom is inversely proportional to that of the ionization enthalpy. It means that the lesser the radius, the higher the ionization enthalpy, and the larger the radius, the lesser the ionization enthalpy will be seen out here. Second factor that will affect is the charge on nucleus. Charge on nucleus. Okay. The attractive force between the nucleus and the electron increases with the increase in the nuclear charge. This is because the force of attraction is directly proportional to the product of charge on the nucleus and the electron. Therefore, with the increase in nuclear charge, with the increase in nuclear charge, with the increase in nuclear charge, it will become more difficult. It will become more difficult to remove the electron. To remove the electron. Okay, and ionization enthalpy will increase out. Ionization enthalpy will increase. Third, screening effect of inner electrons. Okay, shielding effect. It is also termed as shielding effect or screening effect. Shielding effect or screening effect of electrons. Okay, so what is this? In multi-electron atoms, okay, in the atoms which is having multi-electron atoms, the outermost electrons are shielded or screened from the nucleus by the inner electrons. This is known as shielding effect or screening effect. As a result of this, the outermost electron does not feel the full charge of the nucleus. Okay. If D block or F block is present, then this shielding effect is increased out there, because the D block and F blocks are having higher energy than that of the S block and P block. And due to this reason, what will happen? They will have more nuclear charge as comparison to that of the outermost S shell or outermost P shell. And due to this reason, what will happen? A shielding effect or screening effect will be found out there, and hence lesser nuclear charge will be found out there in the outermost electrons, okay, of the S block and P block elements, of the S block and S orbital and D orbital electrons, okay. And hence it will be more easier to remove that particular S orbital electrons or P orbital electrons due to the presence of shielding effect. Okay. Next is the penetration effect of electrons. It is also known as what we also call them as penetration effect. Here we will see that the electron in the S orbital has the maximum probability of being found near the nucleus, and this probability goes on decreasing when we are increasing the energy of the orbitals. Okay, so in case of P, D and F, the probability of founding the atoms near the nucleus, it will start to decrease out. Okay, so in other words, we can say that S electrons are more penetrating towards the nucleus than the P electrons. Okay, we will say that the S orbital electrons, they are more penetrating towards the nucleus as comparison to that of the P electrons. Okay, P electrons or the D electrons or the F electrons. Okay, so hence S electrons, thus for the same shell, the ionization enthalpy will be more to remove a S electron than that of the P electron. Okay, which in turn will be more than for the D and the F orbital also. Okay, let's move further and see the trends for ionization enthalpy in the periodic table. Okay, the trend for ionization enthalpy in our periodic table. So variation of ionization enthalpy in periods. So in periods we will see that the ionization enthalpy is increasing. Okay, in period we will see that with the increase in the atomic number, the ionization enthalpy is increasing out there. Okay, on moving left to right, that is increase in atomic number, increase in atomic number. Okay, in the period we will see increase in ionization enthalpy, ionization enthalpy. Okay, and for the groups moving down in group, due to increase in size of atom, and also presence of shielding effect, the ionization enthalpy decreases. Okay, it means now it will be more easier for the down elements present in the group to remove the electrons from their outermost shell there. Okay, so these were the variation of the ionization enthalpy in the groups and in the periods. So for today we are ending the class here only, and in the next class we are going to discuss for the electron gain enthalpy, and furthermore we are going to discuss about the different more properties, okay, different more properties, physical properties of the elements, and what trends they are following in the periodic table. So for today we are closing the class here only. We will meet in the next class. Thank you.